Rudra to speak few words about Professor Minaketan Das. Over to Rudra.
Jai Jagannath. It's my pleasure to speak a few words on Professor Minaketan Das. Minaketan Das in short period of time, that is 1935 to 1977. He had a lot of contribution to the world of mathematics. In initial days, he worked as an associate professor and later on as a professor at Ravenshaw College, Cuttack. After he was appointed as the vice principal at FM College, Baleshwar, his works can be classified in the areas of analysis as well as probability theory. He was honored posthumously in the year of 1994 by OMS. Thank you.
Thank you. Thank you, Rudra. Now, this is all about short introduction of Professor Minaketan Das. So now, my request my student Sangram to speak few words about Professor Mahendranath Mishra, who is going to deliver a talk on. Okay, over to Sangram.
Good morning, everyone. It's my proud privilege to introduce Professor Mahendra Mishra, member and fellow of OMS, Indian Society for Probability and Statistics, Institute of Mathematical Statistics. From 1962 to 1974, Professor Mishra has worked as a statistician in Government of Odisha Planning and Coordination Department. He has worked as visiting assistant professor at ISI New Delhi, MC Master University, Canada. He was a lecturer, reader, and professor of statistics in Sambalpur University. He was professor at our Institute of Mathematics and Applications, Bhubaneswar. He has worked as president of OMS from 2006 to 2008. Many research papers have been written by Professor Mishra. May I request Professor Mishra to deliver a talk on Kolmogorov's axiomatic approach to define probability and stochastic process. Thank you. Over to sir.
Thank you, Sangram. Now, I requested Professor Mishra sir to deliver a talk. Yes, sir.
Thank you very much for giving me a chance to speak on this occasion, and particularly about this Minaketan Das. Minaketan Das was known to me, and he was only 2 years senior to me in Ravenshaw College and in the Department of Mathematics. And he was working on this random polynomial, and when I met him, and I know many things about this Minaketan Das, and I chose this subject for presenting because one day I was traveling with Minaketan Das in the bus from Bhubaneswar to Cuttack, and he asked me, Mahendra, do you know that this probability theory that you read in statistics is not is erroneous, is very mistake. It is the m by n number of possible cases divided by the total number of cases. And m is the number of possible cases, that means those which are exhaustive, equally likely, and exhaustive, equally likely, and mutually exclusive. But that equally likely condition doesn't hold always. There is another version which is the Kolmogorov has given. Do you know that? I told that I do not know it. Then will you tell me what is that? Well, I am reading it now, and after some days I will be able to tell you. Then I left Bhubaneswar and went to Delhi for some of my research work. And after staying there in Delhi for 1 year, when I came back, Minaketan Das has published one paper on this number of real roots of a random algebraic polynomial. He was working with Professor Ramanath Mohanty. And actually, the random polynomial work was done by Professor Ghanshyam Samal, and he was not in Ravenshaw College at that time, he was in Puri. And later, I worked on the same subject with as my supervisor, Ghanshyam Samal, when he returned to Ravenshaw College. And thus I know Minaketan Das very closely. And he died in a very accidental manner because he was not getting any help for his research work. He was very much interested in doing good research work, but he was not getting any support. He was working with Dr. Professor Ramanath Mohanty and with a fellowship, that means only the government of Odisha fellowship, not the UGC, nothing at that time. And with a loss of pay, he was working there with Dr. Hansen, with Dr. Ramanath Mohanty. And he was actually very much depressed, so to say, because in Odisha, particularly, research is not given any chance, it is not promoted. If you are doing a research, people think that you are mad. And, that is the belief till now also in Odisha. Because there is no agency which gives any promotion or any any encouragement for doing research work in any area. And particularly, I know that how I felt joining as an emeritus professor from UGC after my retirement from Sambalpur University. There's nowhere I could get a entry because they are not paying. The agency was only, the UGC was paying, but people here didn't know what is emeritus professor. And thus I felt very much. And lastly, I joined in Ravenshaw College by the advice of Professor P. Vibhuti Dev, who was my teacher in Ravenshaw College. And his sister, Priyatama Deva, was in the Ravenshaw College at that time, principal. And Professor Deva told to this Priyatama Deva, Professor Priyatama Deva, to give me necessary facilities for joining in the Ravenshaw College as emeritus professor. And that was extended again, and thus I was very comfortable in the Ravenshaw College. This Sambalpur University didn't pay my fellowship. The Utkal University didn't process my application. Lastly, I was disappointed and approached Vibhuti Deva, Professor Vibhuti Deva, who was the vice chancellor of Bernoulli University at that time. This is the situation, and Minaketan Das felt he was criticized. He was humiliated because he was doing research. And one day he was sitting by the Taradonda Canal at Ranihat, where the canal has started, and that is the Fairweather Road in Mahanadi. And he was sitting there, and I do not know how he fell down in that Taradonda Canal, and his body was recovered 2 days before, after in somewhere his body was discovered. This was his situation. He was disappointed. He was totally neglected for doing this research work. And particularly one defect between him was that he got a fellowship to go to USA. He didn't go to universities, he got fellowship in USA for doing research work. He wanted to stay in Odisha and work on the research work. That was his difficulty. And in Odisha, he didn't knew, nor we know at that time, that there is no encouragement in Odisha for any research work. And when Dr. Sudhakar told me that to speak on this Minaketan Das Memorial Lecture, I selected this column of axiomatic approach to define probability and stochastic process because what I heard from him from the bus that was reminded me, and I selected this topic. So it is the Kolmogorov's axiomatic approach to define probability and stochastic process that I want to say. See, in 1958 and onwards, many mathematicians found the classical method of defining probability to be very much unrealistic for general use, and they were attempting to redefine probability in terms of frequency method as developed by Bernoulli. Because at that time, what was the situation? That probability was defined as m by n, the number of possible cases divided by the total number of cases. And this was a mistake. And because the foundation, the definition of probability was not suitable for any applications to the industries and in other branches of science and technology. And so this those who are to use this probability or the stochastic process were not accepting this because they knew that this definition of the probability is faulty. And so many people, they wanted to define it properly so that it can be the foundation of definition of probability will be realistic, and it should be have applications in different branches of science and technology. This type of attempts were never fully accepted, and the stagnation continued by that frequency method. That means the number of possible cases divided by the total number of cases. That was the stagnation was there. Frequency method. What is that frequency method? You toss a coin, head appears, and you get no point. If x1, x2, xn comes outcomes of an experiment in n trials, we define Sn is equal to x1 plus x2 plus xn. Then the frequency method says probability limit supremum of n tending to infinity Sn by n is equal to p, which probability 1, where p is the probability of showing head or the giving coin. Then the question is, n tends to infinity. How long you will go on tossing the coin? Will it be your whole lifetime? That n tends to infinity. Infinity times you will toss the coin. Then your whole life will be spent to decide that the given coin, whether the probability, what is the probability of showing. So how long will you toss the coin to know the probability of Bernoulli, Jacob Bernoulli gave this conjecture, people verified by this experiment. This probability of limit supremum of Sn by n is equal to p, with probability 1. This conjecture was given by Bernoulli. And people wanted to verify that whether this conjecture given by Jacob Bernoulli is true or not. This I have shown in the graph that if x-axis is the number of tossings and y-axis is Sn by n, the frequency of head in tossing m by n, in defining a stochastic process, this is a random walk terminology, and this is represented by means of this path. So what is there? In that, when the number of tossings are 10 to 100, 1,000, then 10,000, and so on. The fluctuation of P is there. The fluctuation of P is there. The fluctuates. And as you increase the number of tossings, the fluctuation gradually decreases, and ultimately it stabilizes. This is the one experiment. Somebody they gave has this experiment that this is the probability. Then what is the probability? Probability is 0.4. Because the point at which this stabilizes, that means this 0.4 is the probability at which the situation m by n stabilizes. When Jacob Bernoulli gave this, people they wondered that whether Jacob Bernoulli is saying the truth. They wanted to verify this by going to this leaning tower of Pisa in Italy. They wanted to go to the top of this leaning tower and throw coins to the ground. And because at that time, the Toronto, the CN Tower in Toronto, near in Canada, was most probably not constructed because it's still higher. If you go to the CN Tower in Toronto, in Canada, you will see half of the USA and on the top of the CN Tower. So people, when Jacob Bernoulli gave this conjecture, people wanted to verify this. Then what happened? The Kolmogorov's axiomatic approach came to, to surpass all these difficulties. Kolmogorov first of all developed the first rigorous approach to probability in 1932. And in 1932, he gave this Kolmogorov's approach. He built up the probability theory from the fundamental axioms when comparable to topology. Probability theory is a measure theory, but uh, it doesn't have that Liebig measure concepts in defining it, and the fundamental axioms of this theory of probability is comparable to the topological space. Modern research in probability theory is closely related to mathematical of theory of sets and measures. And what is that? Axiomatic approach. Kolmogorov started from the sample space, which is same as the previously discussed exhaustive, which I say that it is the n, m by n. N is the exhaustive number of cases, mutually exclusive number of cases, and we denote it by omega. That equally likely, I am not taking into consideration, that equally likely case which was being in defining the probability was adopted earlier is dropped here because nothing in this world is equally likely. Even if you find two twin brothers, or they are also not the same. They are not the same. One zygote, when it is divided into two parts, even they are not same. We have in Department of Mathematics, Joyner and Patnaik, one of our this friend of this Minaketan Das, who had another brother who was also looks like him exactly, but he was a lawyer. So when I generally don't able to distinguish who is who. When I see them, I ask them, "Are you mathematics or a lawyer?" So this was the situation. Here we say that exhaustive number of cases is omega. That means if you toss a coin twice, then what would be the exhaustive number of cases? It will be HH, HT, TH, and TT. That is the sample space. Then if you consider, if you toss the coin thrice, there will be 8 such things, HHT, HTTH, and so on. These 8 number of such cases. So all these elements, HH, HT, TH, TT, are the elements of this sample space omega. Some people say it is sample set or sample space. And these are all elementary events. Here the event is a set. That means HH, what is mean? The first toss is head, and the second toss is also head. HT, the first toss is head, and the second toss is tail. So like that. So they are all events. You are taking into consideration of all events. Next, consider the Boolean algebra. So F, which is constructed uh, from the subjects of omega having the following properties. That means he constructed another set of this algebra, and he called it as Boolean algebra. If omega, that means having these properties, that in omega in F, the null set F in phi is also in F, and omega 1, omega 2, omega 3, omega 4. A1, A2, A3 are elements of this F. F is the algebra that he is considering. Then if A1, A2, AN are all in F, all set in F, then we say that we define that union of these AIs, I going from 1 to N, these are all in F. Well, which you say that closed under finite. If A1 is F, then L complement is also F, closed under complementation. So F is the collection of all possible sets from omega, which is closed under finite union, complementation, as known as the probability measure space. And now we formulate axioms to define probability. Mind you that here this null set is also belongs to this omega. Null set is also belongs to omega. Null set, is an event. Null set is an event. How it is an event? In teaching probability, when I teach probability in my class, I ask students that what is that this null set? It is a set, it is an event. Then what is that event? Null set. What is the question? I get different answers, and which are not correct. Please think about that. What is that null set? Or how it is an event? So we now formulate the axioms to define the problem. Let P be a non-negative set function defined. So P maps F to the real line. P is a non-negative set function which is defined in F such that probability of the whole sample space is 1 and its complementary event I is 0. If A1, A2, A3, A4, AN are elements of F, then probability of union is equal to the summation when AI is phi. When that means when there is joint. When I is not equal to B, we say there is mutually. And the probability of A is equal to 1 minus probability of A. So now here is the question of, we have sample space, F, and we have defined P. So what is the question of equally likely? There is no equally likely. I have defined P on this. I have defined omega, and I have taken the collection of all possible sets from this omega, having that it is closed under finite union and complementation, null set belonging to this. And on this F, I have defined this P, which maps the elements of F to the interval of 0. So what is the question of probability? So where is the question of equally likely in defining this probability? The definition of probability is followed at present. This is the definition of probability defined at present. Stagnation of the set earliest was removed, and the probability is considered as a branch of mathematics. Found applications in different branches of science and technology, and thus the development of the stochastic process, which is a subject which is widely applied in most of the branches of science and technology, and particularly the subject in the Institute of Mathematics, that is the finance that is taught is stochastic processes, the core subject in the stock exchange variations that is taught there. And that type of development of the stochastic process is something different. Now what we have, omega fp as the sample space, as the probability space. Then the Boolean algebra. What is that Boolean extension of this Boolean algebra was later extended to sigma algebra, which is constructed by countable number of sets. Countable number of sets. AI will come on to that. Thus we have omega beta p as the probability measure space. Beta is the Boolean, sigma is the extension of this Boolean algebra. So we have now sample space, omega, elements of omega are the elementary events, collection of the finite number of A1, A2, A3, A3, AI of omega is a Boolean algebra, we will say. That this collection of AI, we will say, is a Boolean algebra. If AI belongs to F, what is F? Yes, script F, that is the Boolean algebra. Then union of this. If AI belongs to F, then it contains the union of AIs. If AI belongs to F, then it also contains the elements, and the null set belongs to that. What is that null set? Null set is also a set. So let the experiment be constructed from the n times. That means W1, Wn, Wn are the outcomes on the experiment. So let A is a subset of this omega. Then Pn we define as Ma by n, where M is the number of outcomes of omega, which lies in A. And Pa is the frequency of occurrence of n of A in n tracks. Then Pn is a map of F201, which is the property that this Pn we have defining as the map from this S, that is sigma algebra, to the element to the interval 0, 1, which is the properties that Pn of union of AI is equal to summation. That means it is finitely additive. AI, when AI is equal to phi, or I not equal to j. Pn of the whole sample space is 1, or the complementary event here of the whole sample, the null set is G. If this is a statistical regularity of observations over where we expect that A in F, Pn will stabilize to a number Pa and shares all these properties Pn. So that when it stabilizes, that the Pn will stabilize to a number P when the number of experiments are increased. When we stabilize the number Pa, we share all properties of this Pn, and omega is the Boolean space, omega P is the Boolean measure space. Why sigma algebra or probability measure space? Why sigma algebra? Till now I have speaking about Boolean algebra. And why do you want to have this defining the probability method space? The sigma algebra, that the extension of this was given by this Kolmogorov from the very experiment of n number of experiments, then it can be extended to any uh, any countable number of cases, which is the sigma. Consider the two experiments having Boolean spaces omega at 1, omega at. So how to describe this in single experiment? If you consider omega 1, omega 2 element invariants in the sample space of omega, Cartesian product omega 2, and the event J1 and J2, J1 F1, J2 F2, then J1 and J2 is the this binary omega 1, omega 2, where omega 1 is J1 and omega 2 is J2. This Boolean algebra to define the probability measure space on this. We know that Boolean rectangles do not form a Boolean algebra, but the finite union of the Boolean rectangles to form a Boolean algebra, which is called the product Boolean algebra F. So we define Boolean semi-algebra as D, and subsets of omega. A B in D, then A product is in D. A in D implies A complement in this Ri, where Ri is D, and this product of Ri and J is phi, or I not equal to J, and your whole sample space is E. The theorem D is an Boolean semi-algebra, then the family of finite disjoint union of the sets in D is a Boolean algebra denoted as F generated by D. So what are to measure on this? Theorem to D is a Boolean algebra, semi-algebra. On this, and a P is a map from D to 0, 1 be a map from such that P, small p, on defined on this D. Omega is 1, probability of the union is equal to the probability of AI by our earlier assumption. So when Fi is a disjoint events of D and the union of EI in D, then there exists a unique probability space Fp on Boolean algebra generated by D, such that P of E is equal to small p of E, where E is. So how to construct this P on D? That this construction is generally given by omega fi I going to one Boolean space, construct the product of Boolean algebra, this Boolean space, product of the omegas, the product of the fi, f alpha. If pi is the probability of fi, does there exist a probability measure P on this, a product of this F alpha, such that probability of the product is equal to the product of the probabilities, where AI is in this Fi? Answer yes. This gives us the theorem that P is defined as above the Boolean algebra rectangles. P is finitely additive and can be extended uniquely to the probability measure in the space F alpha. Hence, product of the sample space, product of the F alpha, and product of the PIs is the product Boolean measure space, and the above construction break down when we consider the following things. That means when we consider this would have been the extension of this Boolean algebra, but this Xn is a sequence of random variables with expectations m, carry on sigma square. Then for any given epsilon and delta, there exists an integer n, so that some minus n less than n, or n such that n is small n lies between capital N and size greater than 1 minus delta for all R, and consider this finite sequence of trials on this, then any outcome is represented by this sequence to omega 1, omega 2. Let omega be the space of all sequences, and the outcome of the nth trial is omega. And omega infinity, f infinity, p infinity is a finite, infinite product of real space omega. Let En epsilon is equal to set of all omegas, then x1, x2, xn by n minus mu less than epsilon, where x1, x2 are the simple random variables in this infinite dimensional space omega. Omega to the power infinity, f infinity, p infinity. Then the weak law of large numbers says probability of En is equal to 1 for every epsilon positive. For this, there is no difficulty, but the stronger large numbers, where E is equal to intersection of n going from 1 to n to infinity and union of n going from 1 to infinity. That means lim inf is this E. There is difficulty in making this statement, since we have not defined measure on countable union intersection of the equals. Consider, therefore, we consider the outer measure, the omega t, the bigger mode space, and the measure space. Omega, let probability of E is equal to the probability of E is equal to infimum of this, Ji union is includes E, then P star is defined for every set of omega, defined as the outer measures of O determined by P, and called the measure of set F. Again, we have that means is the infimum of cover of the sets like F, which contains these, which are the which are in the union of this one. It is the Boolean probability measure space. It's the outer measure. That means it is just like that. It covers, it is, every cover have a finite subcover. So like that. It's called the measure space. And then again, we have that P star of E is equal to infimum of this PIIJ. Ji in F, Ji is a disjoint intersection. Disjoint and the union of Ji is contains U. And P star is J. This is how it is that. The outer measure P star is a countable H subadditive. That is, for this union of this is less than or equal to P star. Then define this set. Omega P star is measurable if for every A in this P star is equal to the AE, and the P star of AE complement. This would be the cancellatory condition. Then the P is subadditive, and that is set P star measurable. A in this omega, P star of A is greater than P star of A. P star of A has. Further, if A is a subset of this, then PA is less than. If P star is equal to 0, then E is also measurable. Considering above the results, we have that when P star is the class of all P star measurable sets, then P star is a Boolean algebra, and P star P star is a sigma algebra, which includes all sigma algebras beta F generated by F. Further, P star is countability on beta. Be able to theorems imply that any measure space P defined on this Boolean algebra can be extended to sigma algebra beta F generated by F. A collection of beta of subsets of omega is called sigma algebra. If it is closed on the countable set of operations, namely union, complementation, and symmetry. In the following theorem, we have P is the measure from D, what we have defined earlier. 0, 1, we measure space in this Boolean sigma algebra D, then F is Boolean algebra of union pairwise disjoint sets in D. E is an element in F. E in union of AI is pi per I. E is defined as probability of AI, and which are disjoint elements. Then P is well defined on F, and P is the measure of F. We have the following extension theorem. That means P is in D is the sigma. Then P is a map from D to 0, 1. We measure on the Boolean semi-algebra, and D is the subset of this. P can be extended to measure on sigma algebra generated by D. Then there exists a measure mu on the sigma algebra. That mu thus we have omega beta is the Borel space. P is the measure on this B, then omega beta P is called the probability measure space, and the probability of the whole omega is 1. And if this omega is equal to union of A and P and finite order, then omega beta P is a sigma finite measure space. Yes. It is a unique also that omega beta P.
You need to speak louder.
Space. If
Speak louder.
If P1, P2 are two measures on this omega F, and P1F is equal to P2F is equal to P2 P of F for all J and F, then P1 of E, P is equal to P2 of E or E in beta F. And this is the completion definition of omega beta P be a measurable space. A subset in D is said to be penal if there exists A in B, so that E is in A and A is a subset of P, then PA is equal to 0. The measured space is said to be complete, and the penal sets belongs to beta. The class of all penal sets is closed under countable linear. So finally, we have that omega P is the measure space, and let beta star is equal to symmetric difference of E and N. E belongs to beta, and N is the P null set, then beta is the sigma algebra, and the P is defined as beta by this P star E delta N is equal to P, whenever E is in beta and P is null set. Then P star is well defined on omega beta P complete mode measure space. This is the completion of omega beta P. If beta omega is the Boolean measure space, then beta is the sigma algebra on the measure of sets, then the measure space omega beta P, P star is the completion of this omega beta P, where beta is the sigma algebra generated by F. This is the extension of the measure on the Boolean algebra to sigma algebra done by Kolmogorov. Okay. Is there any question on this? Is there any question on this to ask? Then I will come to another subject, stochastic process. There is no question?
Sir, could you
There is
please
no
tell
question
me
on this?
sir, reference for reading further this topic?
Eh? What you are
Sir,
saying?
could you tell me some Could you please tell me some of the references which we can refer for?
There is a book by K.R. Parthasarathi, and there is a probability. This is the probability measures on the metric space. They exhaustively define this. And this subject we were teaching in Sambalpur University to the fifth year students. Fifth year means first year of MSc students. This subject was being taught. I was teaching there so long I was in Sambalpur University. This is the starting from the definition, we have come to the extension of the measure from the Boolean algebra to sigma algebra. Here, particular book is given very extensively defining which is the context of this probability. But other measure theory the books are there, they are not suitable what I think. But people differ from me. But I like this presentation of K.R. Parthasarathi, which I was teaching.
Okay, thank you.
Yes, please.
Okay, so I could follow you. I will try to read this book.
Where you will find this book?
No, sir, I can find this book. I am saying I will read this book in future.
Or you couldn't find it?
No. She said she will read it later. She's saying thank you.
Thank you very much for this asking question. Your name, please?
Subhana Bhattacharya, sir. I am in Ravenshaw University.
Acha. Subhana Bhattacharya, you are the students of IMA?
No, sir. I am presently working as an assistant professor in Ravenshaw University.
Thank you, sir. Thank you, Professor Mishra, sir.
Then I will thank you. And I will thank you this stochastic process.
No. 1 second. Someone has a doubt, but there's a lot of echo. Can you please repeat your doubt? Someone named Tarini Charan Panda. Kichi pachachila tomaku.
Oh, you want to ask me something, Subarna?
No. Someone else.
Sir, I already completed my points. Later I may ask. I think somebody else is trying to ask you some question. Professor Tarini Charan Panda, is because his microphone is on.
Is there any question or shall we proceed next? Please.
Major theory book where the extension is done. But on other major theory books, I find that the things are being very complicated. And these 10 theorems that I have mentioned, that these are the very important one and being explained in that major theory of the metric space by K.R. Parthasarathi. Okay. Should I go to the next topic?
Sir.
We speak stochastic process.
Sir, 1 minute. Professor Mishra, sir. Hello. Sir, this is the time we'll proceed the next speaker only. The next speaker is also available with us.
Okay, time.
So should I drop it then now?
Sir, we'll go for next invited speaker, sir, is available over here. So I thanks on behalf of the IMA, on my own behalf, I thanks Professor Mishra for delivering nice talk. So dear participant, we have to go for next invite talk. Okay. Thank you, sir. Thank you, Mishra, sir.
Now, I will not speak on stochastic process.
Sir, we'll meet later on, sir, not today.
Thank you. So my talk is end.
Okay, thank you, sir. Thank you, sir.